Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about space debris re-entry, which is becoming a hot news at this point in time. So let's dive right into it. So what exactly is the problem? Why this is becoming more and more common occurrences at this point in time? Well, it has to do with something known as mathematics, and we are growing, our use of space growing exponentially, meaning last year we used to launch, let's say 10 launches. Now we are doing 100 and we are planning for 1000. So we are growing exponentially, and more and more things are going up. Now, if you remember a childhood proverb, things that go up must come down. That same applies here also, specifically if delta V is not enough. If you have enough delta V, good. But if you don't have enough delta V, you fall back. Now, our atmosphere is a really good shield. That's why there is life on this planet, because if we didn't have that, you will always be bombarded by micrometeoroids and asteroids, large ones, and those things will poof us out of existence. Thankfully, our shield, our Earth, as in 100 kilometers of gas layer blanket that we have, protects us. While this armor is really good, it's not invincible, meaning some things can push through, specifically things that are made by humans. So that does create a scenario where even though you may be like, hey, I'm comfortable, I'm chill, some human-made stuff or even natural stuff can just like yeet inside it. So that does create a scenario where things can fall into Earth. That's why you will have a scenario where it's like, Dragon space capsules service module literally landed on basically Australia. So that's the whole point of it. Our atmosphere, it's good armor, but not invincible armor. So why the heck this sort of things are happening? Well, reality is, even though you may have studied that vacuum is, well, vacuum empty of everything, reality is not that. Now, that simply means there are things in space. When you put a satellite there are things, there are other things that are affecting it. For example, solar wind. Example, high altitude atmosphere. Now, this atmosphere is like above, carbon line. Like, wait a minute, is there atmosphere? Yeah, absolutely. Now, very little, very little. It's not able to do anything with anything, but it is there. And you will notice that whenever ISS is going through the shadow, they will always make sure the solar panels are aligned to the direction of travel to reduce drag. Now, you're like, wait a minute, drag in space? Yeah, that's the whole point. The whole ecosystem, the whole basically sphere around Earth does have gases, and not to mention there is also sun putting some love out there, and not to mention gravitational waves, and waves as in like the Earth's gravity is not completely smooth. It's very smooth compared to moon. Moon is really bad, like good luck trying to stay in orbit in moon. But Earth, while it is smooth, it's not absolutely smooth. So you from a gravitational point of view, you may be going through some bumps, especially if there is giant earthquake on tectonic plates are shifting. These are minor turbulences, but over long term it has more than enough effect. So you cannot maintain orbit in long term. Now, long term depends depending on your height. If you're in low Earth orbit, long term could be few years to 1 century. Mid orbit, it could be like few thousand years to 100,000 years. Geostationary, even longer. And that's why you will always hear people talking about, when we dispose a satellite in geostationary satellite, we'll never put it down, we always put it upwards. So you have geostationary satellite, we fire the rockets, whatever remaining propellant is there, and then we push it up to graveyard orbit, which is above this. Now, like, wait a minute, why we are putting it up? That's the whole point. It takes too much energy to bring it down. I will explain that part also, because you have to understand how the heck things went up there. We put up GG amounts of rocket to push serious amount of payload there. That simply means you have to remove the same amount of energy in order to bring it down. That's why only in animation you see things are going there and like firing rocket and it's going down. Nah, it's not gonna be that easy. Of course, you can have a small rocket and it's like slowly changing its orbit. Like same way we have orbit raising maneuvers, you can do orbit shrinking maneuvers, but those will take days or years or even months or even longer than that. So that's the whole point. So what does it mean? That simply means no matter what you put there, anywhere in low Earth orbit, in mid Earth orbit, or geostationary orbit, sooner or later it's gonna make a choice. Now the choice could be it falls into the Earth or flunks out in the space. That will happen no matter what you do. Only the question is when. That's inevitable. Question is when. So generally, we humans did figure it out very early on that they must have end of life plan, and that's why geostationary satellite from day one always had this idea there. It's like, hey, if we mess this up, that slot is very important, because every country gets its own slot above their sky. So basically, USA cannot put a geostationary satellite in Earth's sky, and Russia cannot put on someone else's one. So like every country gets its own slot. Do not ask about the countries that are very small, but you get that point. Like you get their own slot. That's why that slot is very valuable. And if you have a satellite that is messed up there, you are responsible for removing it. So you have to do. We have end of life plan, but be mindful. Things happen. Sometimes your satellite could just low yoot, and you are like, yep, I'm stuck there. That has happened, and we know that. That's why like there are salvage missions to, basically push satellite away from the slot. So this sort of things happen. Or sometimes you could be unlucky. Let's say, for example, very early rocket stages, we did not think too much about it, so they did not had a fail-safe plan where they will deorbit themselves properly. And sometimes if something could break, you could just have a satellite that's like, we got the orbit fuel, we got everything is sorted, was like micrometeorite hit it and it's like, lol, I'm not gonna work, or something bad could happen. So it's one of those scenarios where something will happen. Now, generally, biggest issue is spent rocket stages. Whenever you're talking about like people tracking space debris, most of the time they are tracking spent upper stages. Upper stages generally have enough delta V that they can get stuck in orbit, and generally they get stuck in elliptical orbit. And most of the time they are not lucky enough where they end up crashing into the Earth. So you will be like people talking about like Apollo era spent boosters are still up there. So thankfully they are big, easy to track. Now then you are talking about spent module, like big module spy satellites. That's why like you literally had a scenario where a radioactive nuclear powered satellite actually crashed in Canada. That happens. So spent modules like that could happen. Satellites are a very common thing. So this is the reality of it. And generally we want to crash things in Nemo point. Now why Nemo point? Well, this point is away from everything, meaning if you aim for here and you miss by hundreds of kilometers, you still fall in nothing. That's where we want to crash ISS. That's where we did crash, if I'm not mistaken, Mir also, and Skylabs. Close enough this area. Again, it's very difficult to control orbital mechanics that well, where it's like, no, you shall hit here, unless it's planned for that. But that's what the aim is. That's why so many satellites are like, falling, and that's why news frequency of this sort of event happening is going up. So let's understand the re-entry side of things. What happens when it actually decides to make love to Earth? So you need to put GG amounts of energy, like seriously large amount of energy, bum amounts of energy. What kind of energy? We are talking about 28 kilometers per second. Let that sink in. 28 kilometers per second. That's not fast. That's not supersonic. That's not hypersonic. That's orbital sonic. That's very fast. And now here's the deal. That's why you cannot like whenever you see animations, people are like, we're gonna collect space junk and deorbit it. You can't deorbit it. You have to remove that much energy. Now, to give you a mathematical context of that, what kind of energy we are talking about? If you have 1 kilogram object, whatever that, let's say just a cube, just a dummy cube, if it's 1 kilogram and you put it into orbit, you have at 1 kilogram at orbital velocity 440 megajoules of energy. Now you may not have context of that. How much is that? Well, you have to understand these things. Fuels generally are far more powerful than boom powders, like things like TNT, RDX, all that jazz. Now, like, wait a minute, then why we use them as boom powder? Well, again, they dump their energy very quickly, meaning if all the megajoules is there, it can dump instantly, and it does not require external variables like oxygen supply. So that's why we use boom powders. Now, those are very low megajoules per kilogram. Then you come to high power fuels like jet fuels, diesel, these sort of high power fuel, they are around 40 to 50 megajoules per kilogram. Hydrogen, the highest megajoule per kilogram, that's around 130 megajoule per kilogram. This puppy is at 400 plus, more than 3 times the highest fuel density you can achieve. Like the only thing that can have more energy than this is nukes. So that's why it's so powerful things, and that's where the energy is coming from. Whenever you're thinking about like a metal object, how the heck it's gonna melt? Like it requires a lot of energy. Metal furnaces consume energy like there is no tomorrow. So how the heck it's melting? It's melting from this energy. Basically, when re-entry starts, you will start to done the math. Basically, okay, this module is, let's say, 13-ton module. Then run the numbers based on orbital velocity, and then you're like, okay, this much megajoule is there. And most of the time, because given the fact that it's higher than hydrogen, most of the time it is enough energy that it will melt no matter what. Even if it's made out of tungsten, it will melt through. Now, that's where the energy comes from. Like whenever you're told like, where is this happening? Where is this happening? That energy is coming from orbital velocity. And that's why you cannot just like, deorbit things, because you have to remove that much energy safely. Fundamentally, it's very difficult. And that's why geostationary satellite orbits, they generally go up, because it's much easier to add few meters per second than to like, remove thousands of meters per second that would require to crash it into Earth. And not to mention, you somehow have to do it very carefully, because there are things below you. So like medium Earth orbit satellites, low Earth orbit satellites, ISS, Hubble, things of that nature. So that's why. Now, not all the time we'll luck out. So we could have a scenario where even though it has energy, if the orbital mechanics do not line up, it will simply not melt. It will get like damaged, destroyed, whatever have you, but it will touch Earth. Now it's like, how the heck it has so much energy? Here's the dumping of that energy is not controlled variable. It's not fixed variable. So things may burn up most of the time. We want like, things going into space and just poofing it, but sometimes it could slow down before it enters into the thicker part of the atmosphere, and just like, it will lose most of its energy in upper atmosphere, like as in like very light atmosphere. So it will become blob, but it will still have enough mass, enough inertia that will just push through. If you have watched the movie Apollo 13, based on true story, as in like that actually happened, they were talking about a scenario where it's like Apollo astronauts, they are coming, if they come at a very shallow angle, they will bounce back. If they are coming at a very harsh angle, they will burn up. Now you're like, wait a minute, why they had heat shield? Why would they burn up? Because heat shield also has a limit. It is designed to handle a certain value. It's not designed to handle ultra maximum pro volume. It's like, bro, relax, give me some gentle time. That's why even space shuttle when it entry, if you look at like animated view of it, it will look like it's doing like this. It's trying to dump off its energy into upper atmosphere before it hits the main, thick part of the atmosphere. And same happens with satellites. Many times satellites end up in a shallow orbit where they're like, they dump a lot of energy but do not completely melt through, completely not vaporize. So you can have a scenario where things make love to the Earth's surface. That's the re-entry mechanics part of it. So how can we solve it? Well, first part is very easy, and we are already starting to. That's reusability, because rocket, again, that's the inherent thing that puts delta V in your satellite. So they have themselves a lot of delta V, and Chinese generally use very high power first stage. High power as in like they are getting most of the oomph out of first stage rather than getting it from the second stage. Now it has some benefits, but also has some side effect. Side effect being that they can launch it in China, and it can fall in Australia. Things of that nature could happen. You just hope it falls in Nemo Point, but sometimes luck does not have it. Sometimes it falls in India. So why the heck that happens? Again, it's too fast to directly fall into ballistic trajectory, but it's not fast enough where it will get a proper orbital start. So it generally crashes in 1 or 2 days, or generally even sooner than that. But it does have the risk of falling anywhere on the Earth. Again, there is elliptical orbits, but you get that point. Like things cannot line up all the time. So generally that's the problem. And second stage, again, it is at orbital velocity, so it will stay there. That's why you will always hear people talking about like spent upper stages of Saturn V is still in the orbit. That's why it was already at orbital velocity. So why don't we deorbit rockets? That will be your common sense. But you have to understand money. When you have a rocket, you're getting paid by the payload, not by anything else. You're getting paid by the payload. So payload requires a lot of delta V. Now, if you have fuel, you want to use that fuel to give payloads the delta V. So what happens when you run out of fuel? You just detach. You're done. You just hang out there. You just chillax. And that's the problem. That's why you could have a scenario where hundreds of spent upper stages could be in orbit. Now, hopefully, most of the time, they generally, because they do not have proper orbital correction, they end up in elliptical orbit, and sometimes they make a love to atmosphere, too much love, and then they crash. But not all the time. So that's why you will hear weird news like, upper stage is crashing into the moon. How the heck that happened? Elliptical orbits. So this is the thing. Now, boosters, they have the biggest oomph there, where it has enough mass that if it hits something on the ground, even on a collapsed state, it can cause serious damage, like crater class damage. Thankfully, it's also reusable, meaning if you want to, as a country, you can make things like this, and that has monetary value. Meaning, if let's say Falcon 9 is like, bro, I can do, let's just go with the numbers, 23 tons to low Earth orbit without any fuel reserve for deorbit burns, no problem. They will do that. They will try to launch it. But here's the deal. What if they're like, hey, we can give you only 13 ton to low Earth orbit, but we'll save the whole booster. Like whole booster will only go to minor repair. So instead of costing, let's say $23 million per launch, it will cost next client, let's say $13 million. They're like, me good, we will do it. And not to mention, very few things actually exceed 13 tons. So that's why people are doing reusability now. That's why every company wants to do reusability, because it's economically viable. And if it's economically viable, people will do it. They will not give a damn about anything else. Second stage is the problem, because it does have enough high speed where even though SpaceX actually did first stage recovery, they did not even attempt first stage 2 recovery, because it will require a heat shield. And that's why upper stage of Starship is requiring so much heat shield, so much mass, so much oomph to it, because it will go to orbital velocity and then it has to deorbit from orbital velocity somehow, so doing it safely while having enough oomph to dump enough energy into payload also. So that's why it's so huge, comparatively speaking. So second stage is big question. Now there are two options for that. First, you make it reusable. Second is you make it so light that it just poofs out of existence. Meaning, even if it touches the atmosphere even a little bit, it will go poof. So that's the aim of basically Neutron rocket from Rocket Labs. So thankfully, this is one of those things that reusable rocket saves money. So it's one of those things that every company wants to do. Every company that has brain is trying to do. And it's one of those things that like, save money. Oh, it also saves our sky. So that's the reusability. That's one of the good pillars. Then we come to what we have to do in long term. Because here's the realistically, do not imagine a scenario where we're gonna send rockets and we're gonna attach to objects, then decel it and then crash it into us. That again, physics does not stop it. It's just like good luck finding a fuel that has enough specific impulse to do that. Best you can do is like send something and then decel it enough slowly, brick by brick. Basically, how we have orbit raising maneuver, you will have to do orbit shrinking maneuver, and hope you do it long enough, reliably enough, and well, good luck. And not to mention, to remove debris, you have to do rocket launches, full-fledged rocket launches with sole object of removing junk. That's not financially viable. But what can we do at this point in time? Well, we have to do what we call better space-based tracking radars. Now, radars have frequencies. Some radars use very long waves, benefit long range, and they can detect big objects like. But generally, military wants to make a high-frequency radar, so they can detect small thing like drones. And not to mention, you're like, okay, then why don't we use ground-based radar that can track things like in outer asteroid belt? Then why don't we use that? Here's the things are very small, like things that we are trying to prevent, they are very small. And frequency wise, you want to use low frequency as I say, high frequency does not travel, so it will not cross 100 kilometers of Earth atmosphere. It will simply not cross it. So if you have a satellite dish, its energy will not go there. So only option is you have to use from space. So low enough density is there, in it's almost pure vacuum. So at that point in time, you can scan a whole sky and get high resolution data of small object. At that point in time, you will be like, dude, that object is gonna re-entry in this place in time, rather than just making a guess. Well, like, that's why you will always hear people like, I think this place will re-entry here, because we cannot analyze it, track it multiple points of trajectory. And high frequency radar does not exist. We have to use low frequency. It's sloppy. The data getting from low frequency is very sloppy. And that's also the same goes for stealth aircraft. If you're like, B2 cannot be tracked, yeah, it can be tracked in high frequency, basically low frequency radars, but it will be very sloppy. You will not be able to get a missile lock on that, and you have to use high frequency for missile locks. That's the benefit of it. It's not like it's invisible to radar. We don't have that kind of physics. High frequency we can. So that's the whole point. And most rockets have to become reusable. Thankfully, this is an economic vector. It's gonna happen no matter what. If any country that is not doing this, they're gonna go bankrupt. So it's one of those things that is done. I'm happy about it. I don't have to think too much about it. Sooner or later, it's gonna happen. So that's good. Design for re-entry incineration. Now, this is one of those things that we have to take very seriously, specifically for medium Earth orbit, because that's a very oopsie kind of place, because things may end up going up or may end up crashing down. So that's a very thoughtful thing that we have to do. And why SpaceX is getting a green light for Starlink, that's the primary reason. They are very low, and it's like passive fail-safe, meaning if their ion engines shut down, it will crash into Earth no matter what. Like, it will crash no matter what, like it will crash automatically. So that's an inherent safety. And they designed the system in such a way that there is nothing in it. Even at like, the worst angle, it should melt very easily. So that's the whole point. We need wiser politicians. That's the part that makes me sad. We do need economic system. Thankfully, it's there. Reusable rocket is economically viable, so people will do it. Politics part, we do need like every country like supporting their weight, basically. India, China, Russia, unfortunately, USA, European Union, all of them have to put very giant radar station, high frequency radar stations in orbit, basically. Almost like instead of spy satellite, we have to put a spy based radar tracking system. And then we can be like, okay, this is the debris, this is where it is. We can make sure no other future collisions happen. And not to mention, we can track things reliably. So if we need to at least coagulate everything into one orbit. So you can have small things, just nudge everything into one junkyard orbit in low Earth orbit, and it's like, okay, just avoid this. And if you have a junkyard, we'll put it there. Then in future, we'll have like, let's say a really powerful solid booster that can give very high G forces, like let's say ICBM interceptors, 100 G. Then you put one, dump it quickly. That can be done. So, but it does require space-based tracking. Without tracking, don't even attempt it. With tracking, good. So this is the things. I'm happy about economical system. I am not happy about the politics part of it, but that's life. So this was my presentation on space debris scenario. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.